Hello and welcome to our webinar, Kubernetes and Containers, a New Era for DevOps. My name is Lauren Delgado and I'm the VP of Education and Marketing here at Platform 9. You know, we hear a lot of buzz these days about Kubernetes, but most of the resources are really focused on the nuts and bolts of the project, not necessarily taking a step back to talk about why this technology is so profoundly important, why it matters, and what it enables for DevOps. So in this presentation, we're going to take a look at what it might mean to your organization in the context of how it works, not just how it works. So I'll come back during the last few minutes of the webinar to help with Q&A, so don't be shy about submitting questions throughout, and we'll do our best to take care of those at the end. With that, it's my pleasure to introduce the CEO and co-founder of Platform 9, Satish Raghuram.
Hi, everyone. Thank you for joining us today. Good morning, good evening, good afternoon, depending on where you're joining us from. I'm very excited to be talking about one of the biggest frameworks and shifts in software development that I've seen in my career. And I do think that Kubernetes represents a fundamental breakthrough in how software is going to be built. And I'm very excited to be talking about that today. In my conversations with Lauren, one of the things we realize is that a lot of the documentation and the information about Kubernetes is extremely bottom-up and down in the weeds a little bit. And this webinar is focused on making you care about Kubernetes in the first place. We'll be doing a follow-up webinar to talk about a deeper dive into Kubernetes and getting started with Kubernetes hands-on. So this webinar is really intended for those who heard of Kubernetes, heard of containers, and are looking at some of these technologies, but want to understand why Kubernetes is important and what are some of the things that it can do for you. So with that, let's go forward to the next slide. So in our landscape today, you've heard of containers and some of the container orchestration tools out there, Kubernetes, Mesos, Docker Swarm. These are technologies that everybody's hearing of, and they're at some level all good technology choices. We're going to be talking about Kubernetes specifically, and we're going to be talking about how Kubernetes and containers are useful to fundamentally shift how software is built. So the first thing I'd like to talk about is how Kubernetes lets you write once and run anywhere on any cloud. So one of the things that's true about, it's a truism about how infrastructure is today is that it is a very fragmented market. There's many different choices. You could be running on bare metal. You could be running on a private cloud, which could be based on something like VMware or based on OpenStack. You could be running in the public cloud, such as an Amazon EC2, a Google Compute Platform, cloud platform, there's a Microsoft Azure, and many others. And the other thing that DevOps teams often see is that they are being asked to be able to be agnostic to some of these choices. So how does one build for a multi-cloud world? And it's not as easy because applications and DevOps tooling are very, very likely to pick up coupling to underlying infrastructure. There's many different ways in which this happens, but here's a few examples. How often have you heard of applications that have been tuned carefully to perform over the years in certain network architectures? There's very specific ways in which routing is set up, load balancing works, and very specific ways in which all of that comes together to deliver the throughput that you ultimately need from the application layer. This could be true no matter whether you're in the public cloud or the private cloud. So the other thing another example of how coupling comes in is, the other way in which coupling comes in is when you have assumptions around storage services and network services. So this coupling is a long-term competitive disadvantage. It only reduces the ways in which you have choices to make infrastructure choices over time. There's obviously economic issues that can come up. Your economic factors as you scale the company, your application grows in usage, or new choices emerge following changes in your business, fundamentally changes. The choices that you made as a startup when you have 100 employees versus when you have 500 employees are fundamentally different. There could also be some really strategic reasons why you may want to have some flexibility in where the application is deployed. For example, you could be primarily an on-premises software company that's running software on premises, but you're being asked to go to SaaS and offer a SaaS solution. The other example is where SaaS companies are sometimes asked to sell to large financial services customers or governments that need this application to be deployed on premises. There could be specific partners of yours that require you to be hosting the software in specific geographies and regions. So these are all examples in which you want to have choices in terms of how your application is deployable anywhere. And this is where Kubernetes is first big advantage comes in, is that it fundamentally eliminates infrastructure lock-in by using containers. Containers run well everywhere. This is not true of virtual machines. The problem with writing a virtual machine-based DevOps stack is that it doesn't work just as well on public clouds as it runs in private clouds, because in public clouds you may need to use nested virtualization, which is almost unacceptably bad in performance. Or if you have to deal with the public cloud native way to manage the application stack, then you now need to deal with two different form factors. There's how you package applications for your on-premises cloud technology, and now you have to repackage those applications in different ways for your public cloud technology. So fundamentally, virtual machines don't give you that level of portability. Kubernetes not only uses containers which run well everywhere, it also provides all of the management capabilities that you need. Containers alone aren't enough. You need the ability, the support in the framework to support all of these DevOps scenarios. So as you see, Kubernetes has support for all of those steps in the life cycle. And this is a pictorial depiction of how that actually looks. So in terms of cloud providers, you could be using a variety of underlying cloud providers, on-premises, public cloud providers. The kinds of resources that these providers enable for you are either bare metal servers or clouds based on that, such as an OpenStack cloud or a Amazon VPC or Azure and so forth. And those are, in Kubernetes, all of these show up as nodes. Nodes are machines, Linux machines, that can run Docker or any other container technology. And you use these machines as a way to consume compute capacity, storage capacity, and network capacity. Kubernetes groups these nodes into clusters and ultimately runs containerized workloads on top as pods. So this is how the technology fundamentally works and lets you write applications and DevOps processes that are fundamentally agnostic to the choice of cloud provider. The second major way in which Kubernetes is a step function is just helping you modularize your application design using containers. So one of the truisms in software is that you see the need for greater modularity in how you build applications. So monolithic applications just make everything worse. They require larger teams because there's just more things that are in the same application image. So there's more people touching it, and larger teams move slower. They require human interaction. They require coordination. Ownership is not very clear. They also create all kinds of spaghetti dependencies. When you have multiple application components in the same form factor, it's very difficult to say where the boundaries stop and what are the rules of engagement for what goes into a certain image versus what doesn't. And then you end up with shared components, monitoring, logging components, and there tends to be lack of ownership because there's so many different people contributing to those because they have to, because it's in a shared kind of space, that lack of ownership creates impedance mismatches, conflicting goals in terms of how changes are made. And it increases the path complexity in testing. So the sum total of ways in which an application can behave and be deployed increases because there's more variability and slow builds. So monolithic applications just make everything worse. Now, containers have the potential of doing to applications just what object-oriented programming did versus procedural languages. So back in the 60s, 70s, people primarily wrote code in C, and in the late 80s and 90s, you started to use object-oriented programming to talk about what is public, what is private, what are the contracts between different modules of software. And these contracts enable greater separation of concerns. It's not that it couldn't be done before, but the fact that this became a first-class entity allowed developers to collaborate around this notion of formal boundaries. And that's exactly what you could do with containers, right? You need to have formal boundaries with a clear separation of concerns so that you can build smaller, more modular pieces of code with greater reusability. And that's ultimately what is the potential for containers. But containers alone cannot do all of this. The problem is that the container boundary does feel very, very similar to the class boundary in object-oriented programming. But you often say, look, take any real-world application that you're working on, and your application probably requires dozens or more of collaborating processes. And in container land, remember that the assumption is that the container boundary gives us a reasonable basis of separation. So you do one process per container, typically, and that's a good thumb rule to follow. But if your application requires dozens of different processes, you're going to need to use dozens of containers. And how do you then weave an application together, a composite application together using those containers? You need some support from an entity that's going to help make that possible. So let's assume that an application can be broken into n distinct services, and each service may require a collection of containers to get its work done. Okay, that sounds like a reasonable way to break this down. Kubernetes does exactly that. It makes it easy to leverage containers to modularize applications. The way this works is that applications are deemed to be composed of services. A service is exposing some focused functionality and is supported by a collection of workers, which Kubernetes calls pods. And a pod is a group of co-located containers that share resources. So an application is composed of many services. Services can be composed of working on top of multiple pods, which are workers. Pods are a group of co-located containers that share resources. So this design, which you can see in the diagram, is what helps you build and modularize applications, composite applications using containers, and progressively modularize your application. So in this example, the client could be another service. This is the box in the middle is a service. Let's call it the booking service for a travel system. And the booking service is exposing, its service name is booking, and its port is 8080, and it's coming from a branch called stable. And the way that works in Kubernetes is that that service, when it runs in Kubernetes, is going to be discoverable via DNS at booking.apps, assuming that apps is a namespace where that service is running. Booking.apps is where any client that wants to communicate with that service can find it and communicate with it via port 8080. But when that client communicates to booking.apps on the network and communicates with port 8080, what really happens behind the scenes is that there's a virtual IP that DNS resolves to, which is routed to, in this case, 3 different pods that are running in the back end. These are the workers which are actually having the business logic for that service, and which happen to have come from a branch stable. That's actually a selector that the booking service is using to designate which pods it wants to work with. So this is how Kubernetes makes it easy to build a modular service and build your application using many different services. And one really interesting thing is that, and it's a common misconception around Kubernetes, is that you need to have a fully microservices architecture before you can use it. And that's not true. The beauty of this design is that you can start with a completely monolithic application and incrementally modularize your application. Because services can be used to represent both Kubernetes native functionality, but also external functionality. So you could take a monolithic application and say, look, I'm going to tear down this application into 5 different services, and I'm going to first port one of these services to use containers and use Kubernetes. And that service could be the booking service. But I have other systems, such as the query layer, the indexing layer, the database layer, the bidders, that are not yet microservices, are not yet container compatible even, and that's okay, because you can use this notion of a service to define this higher level architecture for your application and just port one of those services, which is the booking service, over to be a Kubernetes native service, while the others are actually just pointing to the outside world, to existing legacy systems. And so the beauty of this architecture is that you can start small and start modularizing incrementally and porting to Kubernetes incrementally. And the pods that Kubernetes is actually using for these services support some really interesting patterns that allow you to evolve them over time to be more modular. So some of the common patterns that you should know about, these are some of the patterns. There's many more that you could be doing. One pattern is one of a sidecar. So when you think about a sidecar, think about something that attaches it to a larger car and makes it better, enhances it in some way. So a sidecar enhances a main container. One example of this is an event publisher, something that watches for some activity in the main business logic, like the booking service, and says, hey, when a booking gets done, I'm going to notify someone else. And that could be an event publisher, which is a sidecar. An ambassador pattern is one where you could proxy access to external systems. For example, the booking service needs some data that it needs to load, but that data loader is something that is working as a container in the pod for the booking service, but that data loader could behave differently depending on whether it's a developer who's bringing it up for a test locally versus it's running in production and it needs to actually go query the Oracle database. Adapters enable data normalization. For example, when you're doing schema mapping or ingesting data from different formats, you can use adapters. So there's a lot of constructs here that let you start small, start with a very monolithic application even, and end up over time with a microservices architecture. And the beauty of Kubernetes is that it helps you modularize no matter which stage you're in. From the very beginning to the very end, it can help provide ways and means to modularize your application. So the second major advantage of Kubernetes is that it helps modularize applications using containers. The third one I want to talk about is fault tolerance by design. This is a cloud computing best practice that is how do you build systems so that they are tolerant to failure, especially when you're working in public cloud infrastructure. You want to make a design assumption that the underlying infrastructure is ephemeral and can be taken offline at any time. And in general, this is just a good design principle that helps you build more resilient and scalable systems. The problem is that designing for failure takes a lot of integration. You need to integrate how infrastructure is provisioned and reprovisioned and how applications react to that, and how, when a new node, worker node comes up, how does it get configured with networking? How does it join a load balanced group? How do you achieve redundancy? How do you take an application and scale it out and have redundancy with access to data that is required for all of the workers to be able to work consistently? How do you update an application which is running on hundreds of worker nodes? So these are all challenges that ultimately create integration complexity for how fault-tolerant applications are built in cloud-native ways. One of the big things about Kubernetes is that Kubernetes native services, remember that earlier I spoke about, you could have services which are native, but you could also have services that are just an abstraction to an external legacy system. Kubernetes native services are automatically fault tolerant. They are always accessed via a virtual IP. I showed you the booking service earlier and how it is accessed, any access to the DNS resolves to a virtual IP, which is distributed across all of using IP tables to all of the pods behind the scenes. And these services are visible inside the cluster or publicly via that virtual IP. They're automatically replicated in very, very easy ways onto many ephemeral workers. A pod is essentially a grouping of ephemeral workers, Docker containers, and services are automatically replicated onto many pods. They're automatically load balanced out of the box without really doing a lot of work. Every Kubernetes native service that you run which it could be as all you need to do is really have a Docker container. If you have a service that can be more represented by a collection of Docker containers as a pod, these services are automatically load balanced out of the box, either using Kubernetes' built-in load balancer, or if you're working in a cloud context and you want to use the cloud native load balancer. For example, if you're running in Amazon Web Services and you want to use Amazon's ELB, that works as well. So you can have the best of both worlds, but no matter which you choose, your services are always fault tolerant because they're load balanced by design, and they're discoverable via DNS. The way I described to you, the booking.apps service is discoverable on the bookings.apps name, and that resolves to the virtual IP. So the other aspect of Kubernetes design that you should know about is that Kubernetes is declarative, and it drives current state towards desired state. You declare a state. For example, I might say that the booking service should have 3 replicas, and what you declare is what the desired state is, and it always is till you change it. And Kubernetes observes the actual state that may differ over time. For example, if you're working in a cloud, some of your pods may fail or may be unresponsive. And Kubernetes has ways of detecting that, finding the difference versus the desired state, and converging by actually performing the actions needed to get you back to the desired state. So the beauty of the system is that even if you have issues with the underlying infrastructure, which you should expect to have, you don't really need to do any work to go back to the desired state. Kubernetes does that for you. So fault tolerance, in particular, leverages this declarative desired state analysis within Kubernetes. So let's take an example of how that looks. If you go back to our booking service, if we initially specified replicas to be 2, the booking service would resolve to 2 pods in the back end. But if you were to go ahead and change that to be requiring 3 replicas, then Kubernetes would find that difference, saying that my spec says that I should have 3 replicas for the booking service. I have 2 replicas, so it'll actually go and spin up a new pod. It'll add it to the virtual IP that is being used for this particular case. So the booking service is now load balanced onto 3 replicas. So declarative by design, and Kubernetes finds the differences between actual state and desired state at all times, and it helps you converge automatically. One other very important aspect I want to talk about is that Kubernetes helps you control deployments, not just infrastructure. So, for example, all of these problems show up really in software deployment. I'd love to take your questions and comments on this, but in my opinion, software deployment sometimes reveals the sum total of defects in design, testing, implementation, in how infrastructure is set up, how version management works, and schema upgrades work. Ask your teams that are upgrading to a new version of software, and it tends to be a constant firefight. The problem is that historically, operations teams have had access to infrastructure management tools. So even with the cloud, you have access to Amazon EC2 APIs, ELB APIs, S3 and RDS. These are still infrastructure. And deploying software and updating software to a new version always required DevOps teams to go do all kinds of ad hoc scripting and automation on top. And every organization does it their own way, and probably there's some that do it better than others. But here's a fundamental question. This is the hardest thing in operations, and every organization is doing this in an ad hoc way. That makes no sense. And Kubernetes is the first system that I've seen that has native support for deployments, the concept of deployments. The idea is that you're focusing not on the infrastructure, but on controllers of infrastructure. And the controllers are orchestrating the infrastructure behind the scenes. So, for example, there's other controllers as well in Kubernetes. There's some more specialized ones for short-term jobs and others. But one deployment controller that everybody should know about is actually called the deployment controller. And a deployment controller is responsible for doing things like deploying a new scale-out Kubernetes service. In the previous section, we spoke about how Kubernetes is declarative. Services are automatically load balanced across many replicas. So a deployment controller is something that takes this Kubernetes service and actually deploys it for the first time. it can always give you a status on what is the status of the deployment. Has it completed? Is it in progress? How long has it been in progress? So you can ask someone the question, instead of asking your operations guy, you can ask someone the question in code, where is my deployment? How long has it been running? How many replicas have been upgraded? How many are left to be done? It updates these deployed pods using new versions of container images. So not just your initial deployment of software, but when you have a new version, the deployment controller helps you roll out that new version of that software to your worker nodes. It rolls back to a previous version. Sometimes you find that you released a version and it has an unexpected side effect or a defect, and you want to go back to a previous version. And the deployment controller has native support for rolling back to a previous version. It also has support for pausing and resuming deployments. So the focus here is on deployment management as a first-class entity, not on infrastructure. We're not talking about VMs, we're not talking about hosts, we're not talking about containers, we're talking about your software deployment and the primitives that you want to deal with when you're dealing with a life cycle of software. Deployments provide even more value, and three particular capabilities that a lot of people find very valuable are horizontal auto-scaling. For those of you who've used the public cloud, you may have used something like an auto-scaling group. The idea here is that there is an auto-scaler that can take a deployment and dynamically scale it up or down based on certain CPU or memory resource utilizations, and given some parameters that the autoscaler has been asked to shoot towards. So if it finds that the compute or memory utilization is in excess of what it has been given as the recommended range, then it can spin up additional worker nodes in that same deployment to bring it back towards the mean. And it can do that while staying within limits of the predefined limits of how many worker pods the service is supposed to have. There's also the ability to roll out a new version of software with rolling updates. And people who are new to Kubernetes often find this to be the single biggest feature that they value. The idea here is that you're able to sequence. Imagine that you have a booking service which has grown in time, your business has done well, and it now is running on 450 pods across a bunch of infrastructure. And now you have a new version of your booking service that features something wonderful, and you want to roll out this version. And you want to roll out this version with no downtime to your end users. And you want to roll out this version as quickly as you can because it's got some really high value capabilities. So Kubernetes rolling updates will sequence that rollout across that fleet of 450 pods for you while staying within policy guidelines of how many machine workers should always be spare, or how many workers can be taken offline at any given point in time. So there's some good defaults over there, but you can also tune these parameters using either absolute or relative values. So you're able to say, my fleet of workers for my booking service, this is roughly how much I want as spare capacity when an upgrade is happening, and this is how many workers can be taken offline at any given point in time. And Kubernetes will roll out that new version of the software for you. One other pattern that I want to talk about is a canary deployment. This is a technique that a lot of SaaS companies have used to very, very good effect, where when you have a new version of software, it may have cleared your internal testing processes, but you may still want to get some real-world validation in production from a small set of users before you roll it out more widely. Facebook in particular is probably the first well-known example of how they used to roll out a new news feed, and because it was so controversial, every time there was an update to the news feed, they tested with 100 users and then thousands of users, tens of thousands, then hundreds of thousands, and it would be a very progressive rollout with traffic moving from the older version to the newer version, subject to the newer version performing well. And this is a deployment pattern which is Kubernetes community refers to as a canary deployment, because it's like sending a canary down the coal mine, seeing if there's a problem, and then rolling out the traffic to the newer version only after that validation has happened. So let's jump into one of these scenarios. I'd like to talk about the rolling update use case in particular, And I'm happy to take questions on either the horizontal auto-scaling or the canary deployment scenarios in the Q&A section. So in this rolling update, we have our good old booking service, which is using 3 replicas. And we had the first version, which has been working very well. And our engineers came down to us and they gave us a new version of the booking service that allows people to book with just their Facebook credentials. So this is great. We think that it will be even easier for our users to use. So we want to roll this out. So this is version 2. And what the rolling update feature does is it's starting to create pods. Initially, that pod has no replicas on it, but it'll first create, assuming some default parameters, it'll first deploy 1 replica onto the pod with the second version. Now that pod and that replica is also mapped to the same virtual IP that the booking service is using. So some users will be going to the new version, while some users will stay on the older version. And after that, you'll be seeing one of the pods from the older version is brought down. So you now still have 3 replicas, because remember that we configured this booking service to be running on 3 replicas. And again, the rolling update will trigger the creation of a second pod using the new version, and it'll then tear down the one more pod from the older version. So you still have 3 replicas. So you're alternating between 3 and 4, and you then go on to have 3 replicas, which is our desired state, on the new version, and you then tear down the final version of the old software. So the final pod from the old replica. You're now upgraded to the new version, and all of this happened with no downtime. All of this happened while your users were continuing to use the system, and your users can now use Facebook to make bookings, which is great. So this is just one example of how rolling update works. There's a lot more power and flexibility and tuning to rolling updates. And as I mentioned, there's other capabilities within Kubernetes deployments, such as auto-scaling and canary deployments that are very popular. So we spoke about deployment and native support, first-class support for software deployment. And Kubernetes is really different from infrastructure technologies in that it designs for that natively and helps make that fundamentally easier. And this is one of the biggest pain points that people in software operations and DevOps tend to face. So one more thing I'd like to talk about is running containers in production requires many integrations. So one example is when you're bringing containers up, you need to figure out how are you going to pass certain secrets to it without having those secrets either stored in environment variables or storing them on the disk in the image, because both of those are potential security vulnerabilities. So Kubernetes has support for a special type of volume that is injected into pods and is not stored on the disk to pass such secrets. Kubernetes actually calls this capability a secret, and it has special support to pass secrets down to workers without having them be available in an environment variable or on the disk. Another example of an integration that is very essential for containers is controls on CPU and memory resource utilization that give you quality of service for containers. When containers first came out, a lot of folks who were using virtualization said, but compared to vSphere and other virtualization technologies, containers do not give me the same level of resource control and resource management controls and QoS. Turns out it's primarily a compute and memory QoS that is relevant to containers, and Kubernetes has support for that. One other feature that is very useful is liveness and readiness probes. So imagine the rolling update that we spoke about. When do you know that the new pod, one new version of the pod has come up and is truly ready to take on business? What if there's some initialization logic that needs to happen? So there's a readiness probe, aka health check, which is used to determine that the pod has truly come up and is ready before one of the older pods is brought down. Liveness is a similar concept. We spoke about how Kubernetes is declarative and will automatically converge you to the desired state. Well, what if your software, and software often does this, what if your application service ended up going into a bad state where it was up, it did not die, the node did not die, but your pod was no longer responsive to its API and was no longer responsive to requests that were coming into that pod. If you were only looking at node failures and you did not look at liveness of the pod, you would not know that you needed to tear down that pod and bring up a new pod instead. But Kubernetes knows that because it actually has a way to check for liveness, and you can customize this in useful ways. When you're running containers in production, you want to know anytime there's a failure, there's a fatal termination of a container, you need to know why did it fail and where did it fail, and get some useful debugging information that can make a big difference in how quickly you're able to identify a critical problem. And termination messages help you gather that last gasp from the container before it went away. So these are some of the examples. There's other capabilities as well, but these are just some of the examples with which Kubernetes makes it easy to run containers in production. So those are 5 different capabilities that we reviewed. One question that I'd like to head off, I wonder if anyone in the audience has this in their mind, but one question that is a natural question is, well, this looks a lot like a platform as a service solution, like a, some of the popular solutions out there, like a Heroku and others. Why is Kubernetes different or more interesting than some of those solutions? And it comes down to preserving user choice in a way that traditional PaaS systems haven't. So traditional PaaS systems tend to be limited to certain applications or languages or frameworks, certain application frameworks even. And they tend to be very opinionated about which middleware you can use. And they tend to be restrictive in terms of how code goes from source code to a deployed image. And they tend to also limit choices in terms of how logging works or monitoring and alerting works. Now, these are all areas where your own application development teams may have very strong opinions, or you may have a large base of existing software where it is impractical for you to narrow it down to one version and lose some of the choice here. So that's a fundamental way in which Kubernetes makes it a lot more flexible than traditional PaaS systems, while giving you a lot of the value and utility that PaaS systems gave you. So in summary, we covered a lot of ground, but in summary, Kubernetes represents a breakthrough for DevOps because instead of bolting on operations to applications as an afterthought and in a reactive manner, for the first time, we have a way to think about application design and operation design holistically and think about them end-to-end together. We have easy ways to write applications once, but have them be infrastructure agnostic and cloud agnostic. We have ways to modularize applications more effectively, starting with the most monolithic applications and ending up with the most extreme microservices. And Kubernetes helps you no matter which stage you are in that journey. You have easy ways to build fault-tolerant applications that are scalable and resilient on ephemeral cloud infrastructure. You have first-class support for managing software deployments, not just infrastructure, not VMs, not hosts, not containers even, but software deployments and the life cycle of software, and having first-class support for that, and some advanced orchestration capabilities for some of the most common deployment challenges you tend to face. And you have a lot of the integrations that are essential to be able to run containers in production with confidence and support them from an operations point of view. So I hope you found that useful. I'd like to take 5 minutes and introduce Platform 9 to you. For those of you who aren't familiar with Platform 9, we were founded in 2013, 3 years ago to this day. Today is actually our 3rd birthday, by early VMware engineers. And we've been in production since 2015. We've been having traction globally. We make open source fundamentally easier by delivering it as a SaaS solution. So we support two leading frameworks, OpenStack and Kubernetes. And these are 2 independent frameworks that are both available as SaaS services that you can use with any infrastructure of your choice. That's what we do. We make it fundamentally easier to succeed with open source projects using a SaaS-based delivery model. Platform 9 Managed Kubernetes is probably the product that is most relevant to the audience today. So I'm going to talk about that a little bit. like our OpenStack product, Kubernetes is a SaaS managed solution. We own the SLA on the Kubernetes layer. It's fully automated deployment on our backend. It's deployed by systems with 100% automation, not by people. It's monitored 24/7, and it's instrumented to detect issues and degradations and react to them automatically, programmatically. And we upgrade our customers from one version of Kubernetes to the other, using some of the practices that you actually saw earlier in the presentation today. So it's easy because we own the SLA, we deploy it, we manage some of the heavy lifting around supporting a Kubernetes environment, especially the control plane. We also are providing a solution that is enterprise ready. Kubernetes is a framework that has numerous integrations that are possible. How do you secure it? How do you set it up for high availability? How do you configure the key value store that it is using for high availability? How do you integrate it with single sign-on systems? How do you manage user tenancy? How do you isolate the traffic from different users? All of these are out of the box with Platform 9 managed Kubernetes. These are all things that people who are running Kubernetes in production can do with their own integration efforts, but we make it a lot easier to run in an enterprise context. And finally, as we spoke earlier, a lot of this is really Kubernetes design, but Platform 9 certainly surfaces it up where you can run Kubernetes on top of any underlying infrastructure. So we have customers using this on top of bare metal, on top of Amazon Web Services and other cloud providers. And you're able to define and manage usage and quotas of capacity across all of these clouds. To make this a little visual, this is what the product actually looks like. So this is Platform 9's Clarity UI, which lets you multitask between OpenStack. You toggle left to go to OpenStack, you toggle right to go to Kubernetes. And this particular region on the top right, I want you to notice the Amazon region that this is using. You select the region selector to look at other regions of capacity. I'm logged into a certain tenant, and I'm able to see the servers and storage and network that I've made available to this particular tenant. And the 6 other regions that have different capacity hooked up to them. As you go on to see the infrastructure view, you can actually see the nodes that are earlier in the webinar. I spoke to you about the conceptual model in Kubernetes, where be it bare metal, be it clouds such as OpenStack or public clouds, they ultimately provide resources to Kubernetes, which are Linux machines essentially, on which you can authorize them to be nodes and consume the compute, storage, networking capacity from these nodes. And this is the nodes view. These are a collection of machines, some of which are running in the public cloud and some of which are running in our private cloud that are configured as nodes in Kubernetes. Adding a node is as simple as clicking on the Add Node button on the top right, and you get a simple install or download screen. So click on the top right, and you get a install or download screen that it's a small agent that you download, and you drop it onto your machine that you want to use as a Kubernetes node. And you do this on every machine that you want to bring on board as a Kubernetes node. When you do that, you're going to be able to see those machines come back into your Kubernetes layer and request your authorization. Once you authorize it, they can be assigned to your clusters, and you can use kubectl to perform all of the interesting things with Kubernetes. So that was a very, very short plug for Platform 9 Managed Kubernetes. If you haven't seen the product, please log into our sandbox or reach out to us to try it out and see a more detailed demo. We'd love to hear from you. I'd love to take questions, but before that, I want to share a couple of points of information. Reach out to us today if you found this useful and you're thinking about getting started with your Kubernetes journey. We can help you build your first Kubernetes service and even take an existing application and talk about how to modularize that with some external services and a first Kubernetes native service. So reach out to us, platform9.com/contact, and just reference the Kubernetes webinar so our team knows you were here this morning. Visit our blog. Our blog has some great content around Kubernetes and how it compares with some other alternative container orchestration technologies, including Amazon ECS, Docker Swarm, Apache Mesos. All good choices, but we believe that Kubernetes is very compelling, and in that blog, we try to portray an objective assessment of the strengths and weaknesses of these frameworks. follow us on Twitter. If you don't already do that, we are at Platform9Sys. We have two specific offers that are coming up in the coming weeks. There's the Kubernetes comparison content, which is on a blog, which is being published as an ebook. And so if you follow us on Twitter, you'll know when to get it and hopefully find that a very useful resource. Also, this webinar is being published as a white paper. You have first dibs on this, so it's going to be packaged as a white paper, and you can have the white paper available for download. Find us on Twitter, follow us at Platform9Sys. And with that, I'd like to end my portion of today's webinar. I hope you found this interesting. I hope you're somewhat nearly as excited about this as I am. I do think that Kubernetes is a fundamental breakthrough, and it's going to change the next decade of software development. So I'd like to take questions that you may have. Please ask questions on the panel on the right, and I'll take as many of them as I can.
Great, thank you. All right, well, great timing talking about the comparison ebook, because our very first question is about comparing Kubernetes with Docker Swarm. Can you speak to a couple of main differences between that?
So Kubernetes is really where a lot of the systems innovation in the last couple of years has really been happening. And Docker Swarm has had a couple of rewrites. I think it's now on its third rewrite. And in the most recent version, I was at DockerCon 1.12, love the show, where DockerCon this June or July, where Docker 1.12 was released, where they showcased the ability to integrate some of the Kubernetes concepts via Swarm. I think Swarm has certainly, credit where it's due, I think it has certainly brought a new level of user experience. It has made it much easier to approach some of these service definitions and get started very easily. But when you dig in deeper, there's some fundamental advantages to the Kubernetes approach, which is that you have the ability to have really focused, highly available components that are decoupled from each other. So for example, having a key value store, which is highly available independently and is not coupled with the container runtime and is not coupled with the Kubernetes orchestration layer. That modularity shows up in interesting ways, especially when you try to run this in scale in production. And that's where some of Swarm's challenges will be. But credit where it's due, Docker Swarm does have an easier starting experience. With something like Platform 9 Kubernetes, Platform 9 makes it very easy to start Kubernetes as well. So I'd argue that ease of use is an initial consideration, but not the long-term factor that you should be using. Your long-term decision-making should be based on which is the most resilient framework, has the most open innovation, open community. And in all of these, you see that the systems innovation in Kubernetes is really far ahead of where the rest of the world seems to be right now.
Great, thank you. All right, so the next question is, what are your observations on tools and techniques for managing private Docker registries, hundreds of images, etc.? For example, I am currently using Packer for building VM images on a variety of targets like OpenStack, VirtualBox, AMI, etc. But I am not yet building out or managing Docker containers in an automated fashion.
That's a great question. So that's exactly how I think you do DevOps with a VM. I think that's a DevOps best practice for using something like Packer. We love the Hashi tools here. So using Packer on top of building VM images is exactly how things were being done. And we also did things before Kubernetes. But I would say that now the first step would be to start using a Docker registry. You could set up a private Docker registry, obviously, and publish some of those applications that you have. I would start small, and I would start with a service. Define your service boundary. Try to define the goal as getting more modularity out of your application design and being able to shorten the time to deploy a new version of a certain feature or service so that you see the ROI, your developers see the ROI and the velocity that containers can bring to their development lifecycle, because that will make it self-sustaining. So I would start by saying, in your applications which are running in VMs, it's a little bit monolithic compared to what you could do with containers. Start by defining a service and leave out the rest of the system as external services. and start publishing just the Kubernetes native service that you want to build into a private registry. And the fact that you're doing this with Packer means that you already have a lot of the building blocks needed to build either a Docker file or other ways of building images into Docker. And I think that's how I would start, is make it small, pick a small service that is you're going to try to make Kubernetes native, and publish that into a Docker file, into a private registry, and then use that to build out a service definition with a replica and load balancing, and then start managing the lifecycle, the deployment, the build, deploy, update lifecycle using Kubernetes, and experience the difference for yourself in comparing how it used to be to manage VM images with Packer versus using something like Kubernetes, which gives you a lot higher level primitives. I hope that goes well for you. I'd love to hear from you if you actually try that out, or we can have a conversation offline as well. So please feel free to reach out to me.
Great, thank you. All right, the next question is about the impact of the joint Docker and Microsoft announcement on the deep support of Docker containers within Windows and 2016 Server. Would you like to comment on that?
Yeah, I think it's a good thing. I think the world is a better place because Microsoft is embracing some of the innovation that's happening in the open source and Linux community, and I think it frankly otherwise it makes Microsoft relevant, especially for large enterprise customers that have long-standing relationships with Microsoft. It means that they're able to use their trusted enterprise software vendor, which is Microsoft, with some of the innovation that frankly is a must-have today. If you're not using containers, if you're not using some of the DevOps benefits that these technologies provide, you're at a fundamental disadvantage. So I think the impact is that for the enterprise, it's a great thing that they're able to use these two in combination. Now, having said that, I think that a lot of container traction tends to be in DevOps communities, which tend to be inherently a little more Linux-centric, but choice is a beautiful thing, and this is very useful for large enterprises that have reasons to run Windows at scale.
Great, thank you. All right, the next question has to do actually with the fact that we also mentioned OpenStack. So can you give any examples of use cases where customers are interested in both OpenStack and Kubernetes?
I think that's a great question. So I'd actually like to go back to our first question today, where our participant was using Packer and VM images. Now, if you think about Packer and VM images, it works well with a cloud API. In this case, I think he was using a variety of targets, including OpenStack. So he has an existing application or a collection of applications that are running well with virtual machines on OpenStack. And while Kubernetes lets you use containers incrementally, you can certainly continue to run the rest of your external systems in that existing VM image. You just take out the container native portion now, but the rest of it could run unmodified in OpenStack. And that's an example of how you may want to run both systems in parallel. Now, if you were to say, if you complete the transition and you go 100% all in on containers, would you still need OpenStack? I'd probably say you don't. If you're able to go 100% all in with containers, you don't really have a strong reason to use OpenStack. But we've seen examples of companies. One of our customers is a company called PubMatic. Another customer is a company called Box. You may have heard of that one. They have a decade of source code, and you can't repackage those to be. I mean, it just takes time to be able to repackage these to be truly Kubernetes native, even though Kubernetes makes all of this much easier. So the reality is that heterogeneous environments are very common in the enterprise, and these are both companies where we've seen that they aspire to be 100% container-based by now, but they aren't there yet, not because there's anything wrong with containers, but because it just takes time. And they always have to balance development time between new projects and retooling existing applications.
Great. Okay, that's fantastic. Thank you. All right, with that, those were the majority of the questions that we had. Oftentimes after webinars, we get a couple of trickle-ins on Contact Us, so feel free to do that, please. So I just wanted to mention a couple of really quick items before we close down. The first one is we would love it if you would give us feedback. That's always really helpful. Feedback can come in the form of this particular webinar, but also letting us know about future webinars that you're interested in hearing about. the next thing is just looking forward to continuing the conversation with you. Please follow our blog. Feel free to follow us on Twitter as well. And right back here on Bright Talk. So there will be a recording of this webinar, and certainly stay tuned for future webinars from us as well. Thanks again for spending this last hour with us, and have a great day. Thank you.